Hello everyone, today we will start a new topic, the drainage design. This one is proposed to remove the impact of the water to the road pavement. In reality, water has a significant impact to the performance of road pavements. They are the major cause of fatigue cracking, potholes, and even the collapsing of the pavement structures. The waters on the subgrade layer will cause first heave effect in the asphalt concrete pavement. There will be a lot of alligator cracks and will also generate potholes on the surface of the road. In addition, the waters at the lower layers of the pavement structures will result in rottenness in flexible pavements, which will be the unrecoverable longitudinal depression along the wheel path. From the empirical analysis, we can find that the water contents and moisture are the major cause of distress. In general, approximately 60% of all pavement failures are linked to the moisture. Also, the moisture will cause serious issues for the pavement at parking lots and truck parks. In the pavement, there are many sources of moistures, including the groundwater and precipitation of rains and snow. From our previous analysis, we can see that the moisture takes an important role to the soil properties and some other pavement materials. With that, they can affect the performance of the pavement and induce various pavement distress. From our previous lectures, we know that the water contents will play an important role for the soil properties. In general, increasing water contents will reduce stiffness of the soil and increase the compressibility. Also, it has an impact to the cohesion of the soil. Generally, higher water contents will result in lower internal friction and shear resistance. It can also further reduce the effective stress, which will generate a low shear resistance and high deformation for the soil. Also, if we have some expensive soil, we will observe various heaves with a higher water contents. Considering the freeze soil cycle, you will also see the first heave effect to the road pavement. The water contents also have some effect to the Portland cement concrete. In general, higher water content will result in lower strength and durability of PCC slabs. For asphalt concrete, increasing water contents will reduce strength and stiffness. It will also generate a striping effect, which will result in rough surface and longitudinal cracks. Also, water contents can affect the performance of the pavement, such as rotting, fatigue cracking, and potholes. With the increasing water contents, the strength and stiffness of the lower layers under the pavement will be weaker, and they cannot provide strong enough support for the traffic load. With that, they will cause various distress to the pavement. In the lectures of soil properties, we also investigate resilient modulus at different water contents. The figure here shows the resilient modulus of two soils with different compaction levels at different moisture contents. The gray circle represents 100% compaction of H2 test 99, and the rectangle represents 95% compaction of H2 T99. Basically, we can see that with a higher water contents, the resilient modulus will be reduced dramatically. The pavement deflection is also affected by water contents. From the previous study, we can see that increasing the water contents will result in higher total deflections for various pavement materials, including soils with a different percentage of fines, gravel, and crushed stones. This indicates that the higher water contents will result in larger deformations for road pavement. There are a lot of detrimental effects of water contents to road pavement. For flexible pavement, we know that increasing water contents will reduce strength and stiffness. With that, the water contents will resulting in the fatigue failures of flexible pavement and induce the potential subgrade rotting. In addition, continuous contact with water for the flexible pavement will cause striping of the AC mixed and durability cracking of concrete. This will further cause the functional and structural failures of the flexible pavement, and even result in the collapsing of the pavement structure. Striping is one significant impact of the water to the asphalt concrete. The two figures here compares the aggregates with and without striping. On the left, we can see that once the striping effect occurs, the asphalt binder at the surface of the aggregate will fall apart. With that, it's unable to provide the appropriate properties for the pavement as is designed. For rigid pavement, the mud pumping effect is directly related to the water contents at the subgrade and the base layers. The mud pumping will also lead to faulting, cracking, and general shoulder deterioration of the rigid pavement. In addition, the water contents will cause the potential fatigue crackings for rigid pavement and functional and structural failures, and even collapsing of the rigid pavement structures. The two figures here shows examples about mud pumping and water bleeding for the rigid pavement caused by the excessive water contents at the subgrade layers. In general, there are two resources of the water in pavement. The first one is precipitation. Usually the water will fall to the surface of the pavement and penetrate to the low layers through the cracks of the surface or the joints of the PCC slabs. Second, water table will be another major source of the water in the pavement. Usually the water from the water table will move upwards through the capillary raising effect or vapor movement, and they will enter to the lower layers of the pavement structure. In addition, if the pavement is next to a high ground where the elevation of the water table is much higher than the pavement, then the water there will move downwards and enter the lower layer of the pavement. Moreover, we can also observe some water seepages from the edges of the pavement. Now we know that water may enter the pavement, and it may already be in the pavement. Then the next thing we need to think about is how to deal with this issue. So first, we need to stop it. We want to prevent the water from entering the pavement system so that we can maintain certain amount of the water contents in the pavement. Second, if the water is already entered the pavement, we want to let it go, which means we want to design a system to remove the water as quickly as possible from the pavement structure. Finally, if the water stays in the pavement structure, then we need to find a method to deal with it. Usually we will use the materials and design some features that are insensitive to the water contents. Based on the three steps mentioned in the previous page, there are three methods defined to control the water in the pavement. The first method is prevention. In this method, we will seal the pavement surface and design the surface drainage system so that we can prevent the water entering the pavement structure. The second method is removal. In this method, we will introduce drainage layer or blanket to the pavement structure and apply longitudinal and transverse drain so that we can help the water to move out of the pavement structure as quickly as possible. Finally, we can develop strong pavement sections with a thicker hot mix asphalt or PCC slab, and also apply appropriate improvement of subgrade soil granule-based sub-base materials so that it will be less sensitive to the moisture contents. In real projects, two types of drainage systems are applied: surface drainage and subsurface drainage. The surface drainage is one type of prevention method. In this method, it will design pavement and shutters to stop vehicles entering the pavement structure. In general, it will apply a full-width impervious surface with sealed shelters. Also, it will maintain the surface of the pavement regularly to prevent cracks or potholes. Moreover, in this method, we will apply some special mix, such as open-graded hot mix, which can adequately drain water to the site. And then a transverse pipe will be installed to drain the water away from the pavement. Sometimes the method will also apply curbs and dikes, and if the open channels are not appropriate, then the storm sewers will be installed. With this, it's able to remove the water from the surface of the pavement as quickly as possible. Moreover, it will design the pavement with certain grade so that the water will not stay on the pavement surface. The figures here compares the open-graded and conventional hot-mixed asphalt concrete. Basically, you can see that in the open-graded hot mix, there are more large aggregate particles, and the percentage of the fine in open-graded hot mix is much smaller. The black line in this figure shows the grain size distribution of the open-graded hot mix. Basically, you can see that the percentage of the aggregate particles with the size higher than 9.5 mm is very high, which is more than 70%, while for the fine particles it's very small, less than 5%. With this distribution, the open-grade hot mix is impermeable as well as less sensitive to water contents. In surface drainage, we will also design crown cross slopes for the pavement and shoulders and roadside interceptor ditches. The figure below shows the cross-section of the pavement and the nearby area. We can see that there is a slope applied to the pavement surface and also the shoulder. In addition, a ditch is set next to the pavement. With this setting, we can see that the water forced to the surface of the pavement will move downwards to the ditches. And also with the ditch next to the pavement, it's able to collect the water from the higher ground through the slope. And then the water in the ditches will move away from the pavement. Usually, for the transverse slope, we will set the pavement surface as 1.5 to 3%. For the shoulder, it's set as 3 to 6%. And for ditch, it's set at around 25 to 50%. The grading of pavement is also applied in surface draining method. For straight road segment, we will usually apply crown section, which we introduced in the previous page. In this method, the water will be directed into two directions and enter two ditches at both sides of the pavement. While for the curved road, we will usually design super elevated section. In this design, we will set a constant grade for the pavement surface and the subgrade so that the water will move at the same direction to one ditch on one side of the pavement. The surface drainage method will also design the longitudinal gradient to the pavement. In this figure, we will have the traffic at this direction for the pavement. And for the drainage system, we will apply the longitudinal drain and some transverse interceptor drains so that the water will be collected as the transverse interceptor drain and move away from the pavement. For water control in pavement, if water has already entered the pavement structure, either through the infiltration or as groundwater, then we need to think about the method to remove the water as quickly as possible before any damages occurs to the pavement structure. And to do that, we need to call the subsurface drainage. The subsurface drainage is one type of removal method. Usually there are three types of the subsurface drainage system. The first one is the interception drainage, which is applied to keep water away from the pavement. The second one is the subgrade drainage, which will try to hold the groundwater at a low level. The last one is base drainage, which will prevent the potential floodings to the base layer. In the subsurface drainage method, usually we will apply 3 different drainage installations: drainage layer or blanket, longitudinal drain, or transverse drain. These 3 installations can either be applied individually or they could be applied in combination. The figure here shows the components of the subsurface drainage system. In this system, the most important part is the drainage blanket. For this specific example, we will use the base course as the drainage blanket. Here we will need to put some permeable materials for the construction of the base course. For the removal of the water, it could either be applied with the subbase as a filter, where we will extend the drainage blanket to the subbase filter. And we should apply certain lateral slopes to the pavement surface so that we will allow the water move away from the pavement structure to the ditches. The other way is like we will design edge drain and edge drain pipes so that we will allow a larger flow of water to be removed from the pavement. The implementation of edge drain and edge drain pipe is one kind of longitudinal drain for subsurface drainage system. At some rare case, the edge drain pipe is not necessary for longitudinal drain, but in real-world implementations, the pipes are necessary. Usually we will use the perforated pipe for the longitudinal drain. This pipe is able to remove water with large volume as quickly as possible. Compared with the daylighted construction with a subbase as filter, the longitudinal drain is more reliable and more economical. Also, for the daylighted construction, sometimes it will cause serious issues about the contamination of drinking water and clogging during construction. In subsurface drainage design, we are able to put the drainage blanket at various locations of the pavement structure. We are able to set the base course as the drainage layer. In that sense, the drainage layer should satisfy the strength requirement of the base course and the permeability requirement of the drainage layer. We are also able to put the drainage layer behind the base and the subbase layer, and it will be acted as an actual layer or one part of the subgrade layer. In that situation, we need to make sure that the base layer and subbase layer meet the permeability criteria, which means the permeability of these 2 layers should be higher than the infiltration rate. In that sense, the water can move freely downward to the drainage layer and be removed by the pipes. Ideally, we want to put the drainage layer directly behind hot mix asphalt and PCC slabs. With this design, we are able to remove the water as quickly as possible so that we can prevent any mud pumping effects. However, this will also cause some problem. With that one, due to the fine particles in the drainage layer, the pavement will be less reliable. Also, the waters in the subbase layer cannot be drained away because the drainage layer is actually on the top of the base and subbase layers. The longitudinal drain is also very effective on removing the waters for pavement, which is lower than the original water table of the ground. In that situation, we also want to introduce the transverse drain, which will be applied to intercept the flow from the original water table. The longitudinal drain can also be applied to remove the water from the artesian aquifer. In general, the water from the artesian aquifer will move upwards through the seepage, capillary raise effect, or vapor movement to the pavement structure, and the water will be prevented by the drainage blanket. And after that, it will be collected at the perforated pipe and moved away from the pavement structure. With this design, we are able to maintain certain amount of the water contents for the pavement and ensure that the pavement will keep the desired performance and last for a longer time. So that's all about the lecture today. In this lecture, we introduced the basic concepts in drainage design. In the next lecture, we'll try to finish the rest of the contents in this topic, especially the design procedure. Thank you very much for your attention.